Alors, c'est juste un test pour le micro. Ouais.
Oui, tu m'entends? Il y a des places au premier rang, hein, si vous voulez aussi. Je sais pas. Non, il est pas là pour que ça soit.
Donc, on a ce que là. Le rapport au niveau général, vous avez mis en bas, c'est aussi, autoconsigne, et puis ça pourrait le faire, c'est un rapport technique, à partir du moment où il y a une personne de vidéo, mais c'est peut-être un rapport technique, je vais vous connaître. Ok. C'est la ségrégation de ok. Bon, parler de ça peut être un peu de chance. Là, c'est difficile, c'est deux histoires. Ok.
Oui.
Cécilia, j'ai entendu.
On n'y peut pas, il y a
Ah,
une minute, mais. Ah ben voilà. Et voilà. Bonjour Cécilia, hello. Oui, elle est connectée, ça y est.
je hésite.
Can you hear us, Cecilia?
Good morning to everyone.
Ah.
Can you hear me?
Wait.
Can you see me?
Ok. Just a comment, Cecilia, if you experiment any problem, if you can't hear or if you
Now I can hear you, and I see just a slide with the word limits. Is it right?
I can give you the video. Sorry about that.
Okay.
It's coming.
Yeah, it's going. I can see you.
Okay.
Okay.
Have any problem during the defense? Just you can send me an email. I will be checking my emails or the chat.
Okay.
Thank you.
Thank you.
Okay. So we are going to start this defense. Hello, everybody. I propose that every member of the jury start by presenting himself or herself shortly in order for everyone to know who is speaking during this defense. Then you will have basically time to present your work, and then we will have time for discussion together. So maybe I start because I am the president. Hopefully not the Prime Minister. So I am Pierre Sugerbert. I am a professor of hematology working in Hospice Civil de Lyon in Lyon, France. I don't know many things about your work before reading your manuscript because I am from the clinical field, but I found it very interesting. So I'm very happy to be here and to be president. It's good. So next, maybe Cecilia, can you present yourself shortly?
Okay. Good morning to everyone. It's a great pleasure for me to be part of the commission for the defense of Manon thesis. And I'm professor of image processing and of data algorithms and data structure at the University of Cagliari. I found the Manon thesis a very, very interesting work, and I found a work that was overall very well done. So at the end, after the presentation, of course, I have some curiosity and some question to ask to Manon.
Thank you. So the next rapporteur is Camille.
Yes, so hello everybody. I'm Camille Kurtz. I'm a full professor of computer sciences at the University of Paris-Cité, and I'm working mainly in artificial intelligence and computer vision applications to medical imaging. And I'm very glad to be here today, Manon, for your defense.
It next, Sergios Christodoulidis.
Okay, thanks. Hi all, I'm Sergios. I'm an assistant professor at Central Super Lake at the Mix Lab, and I'm focusing on applying AI tools on healthcare, specifically on cancer care. And I'm also having special kind of focus on images.
Okay, and then your thesis director and co-director, Daniel.
Yes, Daniel Stockholm. I'm an associate professor at the École pratique des hautes études, now part of the University PSL. And I am from the biological field, although now I'm trying to apply as much as possible, thanks to also Manon, the AI in my field.
And last but not least, Xavier.
Hi, I'm Xavier Cagné. I'm professor here at Sorbonne University. I'm from Remix, and I'm the other co-director, co-advisor, more on the computer science field.
Okay, so now the floor is yours.
Okay. So I will share my screen. Yes, can you see it?
I can see. You can start if you want.
Well, so good morning, everyone. Thank you for being here. Thank you for the jury members for having read my work. I'd like also to thank you, my supervisor, Xavier, and co-supervisor, Daniel, for following my work these last 3 years. So today I'm going to present you my PhD project. The title is Enhancing Hematological Image Analysis with Generalizable, Interpretable, and Adaptable Artificial Intelligence Models. So it's a huge title. So to start with, I will give you some background. The white blood cells are produced in your bone marrow they differentiate from a hematopoietic stem cell until they are mature, and once they are mature, they are released in the circulating blood. So here you can see all the stage of the differentiation of the blood cell. And depending on what we are looking at, so you can look at sample that comes from the bone marrow on your top image here, or on a sample that comes from your blood, and depending on what you're looking at, the density of cells is really different, and the type of cell you will encounter is also different because the level of maturity of your cells differs depending on where the cells come from. When a patient has a suspicion of a blood pathology, we will collect a sample from his blood, and there will be a first step that is cell counting. So we will count the different types of cells in his sample, and then we will look at it under the microscope, and this step is called cytology. If there is an abnormality and it's not a normal result, we will go further and have further testing on the blood or on the bone marrow sample. And for this, you will have flow cytometry, karyotype, you can have NGS, PCR. So a variety of tests are performed, and with all the results, you will diagnose a certain pathology. In my work, I will focus on the cytology part, so that's the observation of the sample under the microscope. When you observe something under the microscope, there are a variety of different tasks that are done by the expert and that could be automated. So I will show you what could be automated. First of all, when the expert look at the sample, they will try to determine how many blood cells are present. So you can use detection algorithm. So the detection algorithm will locate your cells with bounding boxes that give you the coordinates, and that could give you an idea of how many white blood cells, for example, there are on your sample. Secondly, you don't need only to know how many there are, but also to count the type of each blood cell that are present. So to do so, there is a specific algorithmic task. It's called classification. The process is giving a label, so name to your image. And in our case, the name will be the type of blood cell that you are looking at. For example, eosinophil, neutrophil, monocyte. So this step is called the blood cell count. And finally, the experts would also want to look at the shape and the morphology of your cell, because maybe there is an abnormality, the nucleus has a wrong shape, or there are some specific patterns in the cytoplasm that would reveal a pathology. And if you want to automate this part, you would ask the algorithm to precisely know which pixel belongs to the nucleus and which pixel belongs to the cytoplasm. And this is called segmentation. So all of this, when it's done by an expert, could reveal a certain pathology. And the purpose is to try to automate some of these processes so that it fastens the process. However, nowadays, the automation is not applied systematically in routine. And this is because the AI still struggles in some really important aspects that makes it, for now, still a bit unsuitable for systematic application. So first of all, I will present you three big limitations in the AI algorithms. First of all, there is a matter of generalizability. Depending on how you acquire your image, depending on where the image comes from, for example, the imaging device, the lighting around, the color agents you've been putting in it, the aspect of the image might vary a lot. So when the algorithm is trained on a certain type of images, it's really often that the performance will drop if they look at image that comes from another data set that will have different aspects. So this is a matter of generalizability. The second point is interpretability. When the expert looks at a cell, they will have really specific criteria to determine what type of cell it is and if there is a pathology. For example, they will look at the color of the cell, the number of the granules, the shape of the nucleus. And it's really important that your algorithm understands these specific patterns in your cell, and that it's not looking at something that is completely biologically irrelevant, for example, the background. So for this, you need some interpretability, and it's even the more important that this is a medical application, so you really want the algorithm to have a medical understanding of what is happening there. And finally, there is what we call adaptability. When the expert looks at a white blood cell, they not only just say it's, let's say, a lymphocyte, they will also establish a lot of different conclusions. For example, this lymphocyte looks normal, abnormal. So it's a variety of tasks that are done by the expert on the same image, and we want the algorithm to be able to do something it has not been trained for. So you want the algorithm to perform a bit out of the box and do something that it has not been trained for. That's the adaptability. So in order to make the algorithm really suitable for clinical practice, I've been proposing 3 different workflows that would improve the limitation I've been mentioning before. First one is a light computation workflow that aims at being able to classify images from any type of dataset. So whatever the aspect of the images, we have a good performance in the classification tasks. The second part is having a multimodal network. So the idea is that I will give not only the image to the network, but also some descriptor, for example, describing the texture, the geometry of my cell, and then I can understand which descriptor was important for the prediction. So that gives some interpretability. And finally, I use a less supervised framework where I add some hierarchy, and this hierarchy provides some biological knowledge and also would make the model more adaptable. I will explain it later. So let's start with the first part of my project, which is about generalizability. As I mentioned before, there is a huge performance drop when the algorithm encounters some image that comes from a new data set that they've been not trained on. So there are some solutions nowadays, and we call it domain adaptation. However, I have noticed that these solutions are mostly computationally intensive, that they can create unrealistic looking images. And that most of the time they need the external data set in the training. And the idea is that I want the algorithm to perform on any data set, even if it hasn't been seen in the training. So first of all, I collected images from public data sets from a wide range of different data sets that have different aspects. And I wanted to classify this image into 6 classes that are presented here. And they were chosen as to maximize the number of shared categories between the data sets. As you've seen, the aspects, the visual looking of the image can be really varying. So first of all, I tried to apply a color transform that would put everything under the same style. So I used the L alpha beta color transform because it's really robust and it's really light in computation. It's just multiplying by 1 matrices. So first of all, you have your red, green, blue image, and you convert it into another space that's called L alpha beta space. In this space, you standardize your image so that it is under the same standard deviation and average as the target style you want to aim at. So here, the target style was images that look like an Olympus VS200 machine with the MGG coloration. That's the type of device we have here that provides really high quality type of images. So here you can see that's the change of the color makes it look like a sentence style image. Secondly, I did some few-shot learning. So I did a first training, a massive training with 2 source datasets. And these 2 source datasets contain 27,000 images. These were all annotated. And then whenever I find a new dataset, I will use less than 100 annotated images, and I will do some fine-tuning with this new target dataset so that I have good performance even with a few annotated images. So that's the fusion part. Now let's jump to the results. First, you can see here it's really visual assessment, but we can say that the visual style is really consistent for all the datasets wherever the image comes from, thanks to this simple color transform. And secondly, we've done some classification on the target dataset. And for each target dataset, we have a classification results that is above 80% and even sometimes above 90%, which is quite satisfying, knowing that we had less than 100 annotated image per dataset, which is a few, and that's also relieved the annotator from a cumbersome annotation process. We wanted to compare our workflow with other possible workflow, for example, without the fine-tuning, or for example, without the color transform. And in the end, we found out that our workflow, so fine-tuning plus color transform, gives the best results. So that's was the end of this first project. And we perform a final error analysis. So the idea is to look when the model is wrongly classifying a cell, why is it so? And we've seen here that neutrophils that are predicted as eosinophils, you can see here the 2 cells, mostly show some red cytoplasm pattern. So now the second question we ask is, what are the prediction criteria? And this gives me the transition to my second part, which is interpretability. The matter of interpretability is really important when you talk about deep learning models in general. And what is gold standard now to give a bit of interpretability is what we call salience maps. So the idea is that you will highlight the pixels that are important for your prediction. However, we can see that most of the time the highlighted zone is not so accurate, and that also there is no quantification on how this pixel was actually impacting the prediction. This is why I came with a second model that I will present to you now. First of all, I segmented my cells so that I know exactly where lies the cytoplasm and nucleus of the cell. So I had 3 different types of data sets, and I compute the intersection over union, which is a metric that tells me that the segmentation prediction are quite high. So that's the first part. And now that I have the exact idea of where is the cytoplasm and where is the nucleus, I can extract characteristic morphological attributes from the nucleus and from the cytoplasm. So the first characteristic I extract are geometric. I will compute from my cell its perimeter, area, roundness, circularity, and eccentricity. Secondly, I will extract some color attributes. So when you look at an image, let's say in red, green, blue, each channel, for example, red, it's a distribution of pixels that will tell you the intensity of red all over the image. So from this distribution, you can also extract some attributes, for example, the mean, the skewness, the standard deviation, the entropy, and the curvature. So I did it for red, green, blue pixels, but also for other types of colors like cyan, magenta, yellow. And finally, I extract some texture attributes. So if you remember, the texture of the cytoplasm and nucleus is really important because it gives you information about the type of cell and possible abnormality. So I used two two operators for the texture attributes. The first one is the linear binary pattern. Here, for each pixel, you look at how it looks like surrounding pixels. So this is more neighborhood type of attribute that would give some local pattern. For example, a line or a corner or an edge would have different type of behavior. And secondly, I go for the gray level co-occurrence matrix that would more say if a pair of pixels appear often or not, and that would give you an idea about global pattern of your image. For example, if there are stripes or squares or something that is more global, then that would be revealed by this gray level co-occurrence matrix. This is the architecture of the network I have used. So the most important part here is that it is multimodal. So it takes both the full image as an input and the descriptor I have been mentioning before that comes into another branch. And then at the end, I have the prediction that is the cell type. So what type of cell is my image? And the main interest behind it is that when I use the morphological branch, I can compute from here what we call the sharp values. So the sharp values are a specific operator that would give you the importance of each feature for the final prediction. And then you can extract a graph that I will present to you later. Now I will show you the results. So here I have three data sets, Rabin, Acevedo, and Tianjin, and I compared three setups. One is if I have only the morphological attributes, what are the predictions? If I have both morphological attributes and image, so that's the multimodal framework. And finally, if I use only the images. So what you can see here, all the results are in average really high and very close, but still in average, the image-only framework perform a bit higher. However, what is really interesting in our case is that we use the multimodal not only for high performance, but also for explainability. That is the purpose of this framework. So why is it interesting? Now I can extract from the multimodal network the sharp values. So what you see on your left, this is by order, all the important characteristics that were relevant for the final prediction. So this is for an eosinophilic cell that you can see here that is characterized by its really reddish cytoplasm. Yeah, I mean, among other characters. So here you can see if the feature is high, it means it was highly contributing. And for example, for this one, if it is red on the right, that means that is a high value that was contributing for these predictions. For example, the perimeter, when there is a high perimeter, we have a higher chance of having an eosinophilic cell. So here I put on the right a summary of the important features that you can see. First of all, what is important is that we have a high standard deviation and average of yellow and red colors. And this is interesting because the granulation in the eosinophil are orange or reddish, so that's why we believe the yellow and red were important. Secondly, it's important that the perimeter is high of the cytoplasm and that there is a good circularity. And finally, the texture has to be really heterogeneous, which is presented by the cytoplasm that can reveal the fact that the cytoplasm has some granules in it, and that could make the texture heterogeneous. So in this second framework, you saw how we tried to improve with the explainability. And now we will see the third part of this PhD, which was the biggest project in this PhD, actually, about having semi-supervised learning with hierarchical classification. So in my third year PhD, I think there's been a rise in the trend of the foundation models because they've been performing better and better. So the idea of what we call foundation models is that they are able to perform tasks for which they were not been trained. And this is interesting in our case because, as I mentioned before, we want the model to be more versatile. Also, it's good because they are mostly trained without annotation, so you do not need experts to annotate every single of your images. So that's also relieved the experts from this annotation process. So this is what we call the self-supervised model. However, this of course poses a problem because if there is no expert knowledge in the training of your model, you have the risk of missing some important biological, for example, patterns, because you're not driving the model into a specific direction. Secondly, so this is why we tried to add some supervision, so some knowledge into the model to have it more biologically related. However, when we do it, we encounter the new problem. It is that we have different data sets and they don't use the same precision in the way they annotate their image. So sometimes they would say this is just a lymphocyte. Sometimes they would say this is a large lymphocyte that has some pathological features. So we have these different degrees and precision into the annotation, and we want to keep as much information as possible. This is why we use this hierarchy. So I will start first by this let's supervise framework. The foundation model we are using, the architecture is called DynoV2. So DynoV2 relies on an augmentation. When you take the original image, you will produce multiple versions of the same image by introducing some modifications. And these modifications are called global crops and local crops, depending on how much of the initial image you keep in the end. And then what you have here are the views of the image, that's all the modified version of the same original image. Secondly, you will give them to the model, but it's not just one model that you will use, but two models, the student and the teacher. The student will receive more information than the teacher because you will give him both the local crops and the global crops. Then you want the student representation of the image to match the teacher representation of the same image. So for this, you use a dyno-loss, and we call it cross view because you want the representation of the image 1, for example, from the student to match the representation of the image 2 from the teacher. So this is why we call it dyno cross view. So here, the idea is just to match the representation of the two models. And it is called distillation knowledge because you will then update only the student weight with the backpropagation, and there will be an exponential moving average so that the student weight are infused to the teacher thanks to an exponential moving average. So only the student will perform the backpropagation process. Secondly, you will not only give different information, you will also mask the image. So you will put random patches on your images so that the students see masked images and the teacher see unmasked images. And samely, you want the representation from the students to match the representation from the teacher. And this is called in view because now you will align the same view from the student and from the teacher. So why is this interesting? In general, the masks allow you to understand local patterns, so some small thing that could be present in your image. So that's why you use this one. And the former task is more about having some more global patterns, so how the image generally looks like. So this is how DynoV2 works in general. So it's not supervised, and it uses the dyno-loss and the ibot loss. And I added supervision into this model. So the final loss will have the ibot, the dyno, and a supervised loss that corresponds to adding some knowledge into the model. So there are multiple ways to put supervision into a model, and I tried to compare different ones. First of all, I used classification. So classification is the idea that your model has to predict what type of cell it is seeing. So I put a head on top of the teacher, and I perform some classification with the traditional laws that called cross-entropy. Secondly, I used supervised contrastive learning. So here, instead of predicting what type of cell it is, the idea is more of grouping cells that share the same label together and putting apart the cells that share different labels. So it's more of a distance task where you try to put together things that share the same label. And for these two tasks, the supervised contrastive and classification task, I have a hierarchical version where I add some hierarchy in my labels. So you've been hearing hierarchy a lot. Now I will explain you exactly what it is. So instead of having all my type of cell in a, let's say, linear flat, it's called flat way, where they all have the same rank, I will now try to group the labels of my image, so the cell types, by categories. So here you have a 4-level hierarchy. First, we group them by lineage, then maturity, cell type, and morphological characteristic. So every time you jump to a new category, a new level, it's a subgroup of the former level. So for example, lymphopoiesis, this is immature lymphopoiesis and mature lymphopoiesis. Why is it interesting? First of all, you can include all the labels. I mentioned before that there is variety in the degree of precision in the annotation. For example, in some data sets, you have the annotation of the cell is just neutrophil. And then in some other data sets, it's band neutrophil and segmented neutrophil. So they go further into the description of which neutrophil it is. And I want to keep all this information. So this 2-level possibility gives me the opportunity to keep all the labels. The second reason why it's interesting is that now I have made some categories closer to each other. So it's supposed to better represent the biology of the cell. So for example, now the cells are grouped by their lineage, and this has some biologically relevant aspects. I will try to explain you how you include this hierarchy in the training of a deep learning model. So if you were using classification, so remember there were classification and supervised contrastive. So I start with the classification part. So if you do classification in a traditional setup without the hierarchy, let's imagine your cell here is a segmented neutrophil. You have a label vector that is 0 everywhere, except on the class that is true, which is the neutrophil segment. Then you have a prediction, and the predicted vector will give something that you can imagine as the probability of prediction for each of the categories, and the highest probability is given to the segmented neutrophil. Now you will compute the difference between the prediction and the label with a loss that is called cross-entropy. So to do so, you multiply the first vector by the logarithm of the second vector. This gives you the formula of the cross-entropy. And what appears here is that, so this part will influence the loss, so the probability of neutrophil segmented, but all the other probability, because they are multiplied by 0, they will not influence the final prediction. And here we are missing some information, because maybe if it was predicted as a band neutrophil, which is a really close type of cell, that would be less severe than it was predicted as an eosinophil. But here, the prediction that influenced the loss is only the one on neutrophil segment. So this is where my hierarchy plays the game. So here you can see the classes are not anymore represented in a flat way, but in a tree. So in this tree, you have the same prediction as before. So for example, 0,9 on the segmented neutral field, 0,7 on the base neutral field, but they are represented in a tree. What we will look at is the edges that connect the different levels of my hierarchy. So for example, if I look at this edge is actually the probability of having a segmented neutral field, knowing that I have a neutral field. So to compute this probability, I will have the probability of segmented neutral field over the probability of the neutral field, which is the sum of these two probabilities. Now, to compute the final loss, I will use these two edges, so all the edges that lead to my final prediction, and I multiply them by a parameter lambda that gives you an information about how high or low we are in the hierarchy, so that you can penalize differently mistakes depending on how high you are in the hierarchy. So this idea comes from a package that has been released by Bertinetto in a really cool paper, but the problem is that in their case, they only considered what we call leaf classes. So a leaf is an extreme node. It's a node that's at the end of your tree. And if you remember, my problem was that for some time, the precision of the label was not so good, so I had a non-leaf prediction. For example, the neutral field could be a class that is valid. So in this case, I made a modification in this package so that I can include some non-leaf nodes as prediction. And what would be used for the probability is the edge that lead to my node and all the edge that are children to my node, so that are under my node. So this is the final formula with the modification. Secondly, I implemented some supervised contrastive learning in the Dino D2 framework. So remember, the supervised contrastive is about pulling together images that have the same category, so images of the same type, and pushing apart images that have a different type. So for example, here, all the eosinophils are brought together, and these cells that are lymphocytes, they are brought apart. So that is what we call supervised contrastive learning. Now there is a hierarchical version of this. In this case, you have two types of positive. So positive are the images that are brought closer to the image that are attracted to my image of interest. So the first type of positive, they are the same as before. You can see them here. They are the eosinophils. So these are positive because they share the same category as the image we are looking. And then there is another positive, for example, the neutrophil here. It's positive because it shares an ancestor. They are both granulocytes, so they have an ancestor in common, so it's also positive. And now what happens is that the positive one, they are strongly attracted because they share the same category, so you want them to be really close in your latent space. And the positive 2 is less strongly attracted because you also want it to be a bit closer in the latent space, but it's still not the same type of set, right? And there is a margin here so that this image cannot go closer to my image of interest than images that share the same category. So all the eosinophils will be really close, and then just after, you will have other, for example, neutrophilic cells that are still in the same lineage, but a bit different, so they will not be closer than eosinophilic cells. And finally, you have the lymphocytic cell. It's still pushed apart because it's negative. It doesn't share any lineage with my eosinophil. So this is the hierarchical loss. And I will just show you the metrics we use. So we want to see if the prediction align with the hierarchy we are implementing. So we, for this, use what we call the lower common ancestor. So what is really interesting with the hierarchy is that now you can measure the severity of your mistake. If there is a mistake, is it a severe mistake or is it not so bad? So for this, you will compute, for example, if this is a band neutrophil and it's been wrongly predicted as a segment in neutrophil, what is the height of their lower common ancestor? In this case, it is neutrophil, so the height is 1, so it's not such a bad mistake, right? And we also have a hierarchical version of precision and recall that gives you the F1. I just show you what is happening in the embedding space. So this is for an external data set. When we have the non-supervised model for this data set at least, there is a good clustering of the images by categories. And when we add the hierarchical supervision bits, what we see is that the groups are more defined depending on the subgroup we have been putting. For example, I differentiated between the mature and immature granuloids. So now they are further apart because I asked them to be further apart with the hierarchy. Also, the monocytes, they are a different lineage, so now they are also brought further. I evaluated with some metrics. So 2 evaluation tasks. The first one is the clustering good? Are the cells grouped according to their cell class, their cell type? So what we see here, this is for nearest neighbor evaluation for weighted F1 score and balance accuracy. This task worked very well. So there are also other tasks that were working a bit less accurately. So in this case, we see that the hierarchical cross entropy is giving the highest score, both for the weighted F1 score and balance accuracy. This is the blue bars here. Second task, the question is, okay, are the cell types clustered together, but also are the cluster aligned with the hierarchy? Are the cluster grouped in a way that aligns to the hierarchy I've been imposing? So for this, I look at the lineage accuracy. So what's the accuracy of the prediction according to the lineage? Same, the hierarchical setup is working the highest, and hierarchical F1 score is also giving the highest performance. Final part is LCA score. So we have the hierarchical cross entropy is also, it's among the lowest. However, there is still, it's still quite unclear which one is performing the best between unsupervised or hierarchical cross entropy. And we think it is maybe because this dataset in particular, it has a really well-defined classes that may be well coached by the model, even without the hierarchy. This leads me to my conclusion of this 3-year work. I just first want to mention some limitations we had in our work, and which I think are also strong limitations for anyone who would want to go into this field and perform the same type of tasks. First, a problem of accessibility of the data. That has been a huge issue. So there are some publicly available images, but they do not represent all the diversity of cells you can find in your body, especially the bone marrow datasets are more scarce, and the rare cells are scarcely represented, and some pathology are not represented in the public dataset. Secondly, in blood cytology, there is no available report in public dataset where you can also have some more information about the patient or some genetic data that would give you some complementary information when you want to do some classification. And finally, there is a lack of standardization. The imaging devices available are really multiple, so everyone has different type of acquisition that gives to the resolution. The staining can also be varying, so this is why you have a huge variety of type of images. And there is no regulatory framework that could be shared in in France that could be could show that you have it's easy to make your data available. I want to end it by showing the contribution of this project. The first part was about my simple workflow for generalizability, and I think it is interesting because now that foundation models are becoming more and more popular, they suffer a lot from this problem of generalizability, especially they suffer a lot from batch effects. So this is still a really interesting matter. Secondly, there is the multimodal network for interpretability. So this also is interesting because the large multimodal models, which are really also popular nowadays, they also need some more explainability. So that could be a way to improve it. And finally, the introduction of biological knowledge into a foundation model is, I think, pretty important for medical application of AI. So in general, these three aspects of my PhD were really aiming at having real-world application of AI in clinical practice of hematology. And to conclude, I show an example of how this could be in practice applied. For example, this is a type of model that could give some prediction of pathology when looking at the sample, and that could also give some important information that you would have to focus on your sample. So the idea of this framework is that it is multimodal, so it doesn't take only the image based, but it also takes the text, so the report of the patient, and other blood test results. Because at the beginning of this presentation, I showed you that there are multiple tests that are done on the patient, so you could also use these results. So in the image part, the model would look both at the entire slide and give an information about this slide, because the slide is important because you want to know the population in general, right? You want to know there are a lot of white blood cells, there are a lot of lymphocytes, so something that is more global, that gives you an information about the entire slide. And also some representation of important cells in your slide, so it's more a cell level embedding, and this information would be integrated in the form of a hierarchy, as I showed before. For the text part, we could extract the report and some attributes in the report, like are there any hour rows in my cell or some fagot cells, and that would also be given to the model, and the other blood test results. And finally, this would be integrated into a large network that would, thanks to a large language model chatbot, allow some interaction with the user, who could say, now I have a new blood test result, for example, how would you adapt to this new information? So some types of interaction. So this is an idea of a really big model that could be of huge help if it was working well. This brings me to the end of this presentation. I want to thank you for your attention. Here are the publications that have been written during this PhD, and I would like to mention that this has been done with a lot of collaborations, notably between LIMIX and Professor Delemot lab in Saint-Antoine, as well as some collaboration with a lab in Munich, that is Helmut's Munich lab, where I have been spending 3 months, and I've been working with them for the entire year. Thank you very much.
Thank you very much. So I propose to start with the two rapporteurs, then the examiner, sorry, then the PhD directors. So maybe Cecilia, if you are ready, we can start with you. And for everyone, if you want to ask questions anytime, I see a good idea. We can have an open discussion.
Okay.
But Cecilia, please.
Should I still share, maybe?
No, I think it's better like that. It was okay.
Okay. Thank you, Manon, for your very nice presentation. I just want to ask you a few questions. The first one is about the issue, the problem of possible overlapping cells present in a slide. As you know, a clump can occur not only in the full slide images, but also in single cell images. Because in your work, you have supposed that the considered images contains only a single white blood cell. But what happens if you find a clump inside of the cell? So have you thought of a possible solution to the problem of clumps that can occur also in a single cell image? This is the first one question.
Yes, it is a really good question because, so as you say, most of my image contain a single cell, but
Yeah.
especially for the bone marrow sample, you have a high density of cells and you can have some clumps. So I think there are multiple ways of seeing it. So either you have the chance or the choice of having some really nice area in your bone marrow sample, and you can do some classification and just remove the clumps, because the clumps can involve some distortion of the cell. So if you have the choice, it's better not keeping the cells that are too distorted, because that might change the aspect in a dramatic way. But sometimes it happens for us that we don't have the choice. The entire sample has a high density of cells. So of course, if you have many images and that you give the label to the center cell, you can imagine that at one point the algorithm understands that the center cell is important. And then we've been trying to do some segmentation network in this case, because at least you would really make the limitation between the background or the other cells that are around on your cell of interest. But this was also really challenging because when the cells are clumped, the segmentation can be really problematic. And I've been trying different options in this case. The first idea was to use the self-pose model that works like a pencil, like you have a center probability, and then you see how the surrounding pixel can belong to the cell or not. But that was not working so well, and I think in the end, a really good model would be it was to use bounding boxes, so a detection model first, and then the segment anything model from I think it's Facebook, that has been released about 2 years ago. That is really well performing when cells are clumped. So that's also an idea.
Okay, thank you. Can I ask another curiosity?
Yes. Yes.
Okay, thank you. You presented a work to enhance domain adaptation for the classification of white cells. You used two datasets for training that are Ivesedo and Munich dataset. And both of the two datasets contain only peripheral blood samples. Why? I mean, could the choice of this dataset be motivated by the fact that peripheral blood data are more readily available or more representative for the classification problem? And do you think that using bone marrow data could potentially improve performance?
Yes, this is a really good point. So we were not really happy.
Sorry? I have a problem. Can you hear me? I have a problem with the meeting. The video is frozen. I can't hear you. Can you hear me?
Can you hear me?
Yeah, now I can. Sorry. I don't know if it was my fault or your fault. I don't know. Anyway.
Okay, I can say this again, but so we wanted really high quality data set for the training because we thought it was important that the initial training had a really high quality of images and the unique data set because there is a higher density of cells because the lighting is a bit poorer. We thought for the training it's not ideal. And also that it would show really good generalizability, that it has not been trained on blood, but it still performs on bone marrow. But I think now that there are more available data sets with bone marrow cells, I think it would be interesting to include this as well for the training. I agree.
Okay. I have a last question, if I have the time to do it. It's about the multimodal approach. And the question is about the multimodal network you propose that is based on images and morphological features. Okay, the problem is this. It seems that combining morphological features and image features appears to degrade the classification performance. Could you explain why this happens? For example, it could be related to factors like noise, redundancy, course of dimensionality. Could you explain the reason for this?
So it's a more hypothesis, but the first reason I think is there is some kind of a redundancy in the information we provide because the morphological features actually already present in the images, and we're just trying to tell them again. So that would be good if the model was not already able to find this characteristic by itself, but because it does, we can imagine that there is some kind of overfitting about like the two branches providing some redundant information. So that's I think also the efficient net model is known to perform really well as itself, as a convolutional neural network for prediction. So maybe they did not need to have an additional branch for having good performance. That was the hypothesis, and also the feature we used. They are really how would I say, really morphological in terms of mathematics, but biologically we could introduce more features that would be more biologically related. For example, the density of the chromatin or the number of granules, and this would be maybe better feature for describing the cell.
Okay, thank you. I don't have any other question. It's enough for me. Thank you. Thank you.
Thank you, Cecilia.
Thank you, Cecilia. But if you have other questions during the rest of the talk, you can of course.
Thank you.
So the next one is Camille.
Okay, so thank you, Mr. President. Before to start, I want to warmly thank the advisors to invite me to review your manuscript. And I want also to congratulate you for this very nice foundation. It was very clear, very pedagogical, with nice illustrations, and I think very complementary to the manuscript. So congrats. I will ask you a few questions. Maybe I will go chapter by chapter, so part by part. Yeah. I will start with the first first part of your work. I have a question maybe that can somewhat overlaps with the previous questions from my colleague, and it is also about the impact of the context in the image. Since you focus on single cell, sometimes in one image you can have a neighborhood cell. I want to ask you if this contextual information can be used somewhere to improve also the task.
Yes, that's a really good question. So actually, there is an interesting thing, is that because some papers have, they had the idea of, segmenting the cell and doing the classification with the segmented cell, because they would think, the background is not of interest. So but actually the performance were dropping. So there is some kind of information provided by the cells around, even if the cell of interest is in the middle. And first of all, I think there is a matter of size, actually, because if you compare your cell with the red blood cells that are around, you have a better idea of the size of your cells, because there is, yes, the red blood cells are overall always the same size. And also, as you mentioned, so in this, that was not presented in this PhD, but we also did some work that was more like patient level work. And in this case, the context is very important, because all the cells, they belong to the same patient, so you have more global information. But then in the data set we were using, mostly you do not have the information about which patient they come from. So, and every cell is a tiny, right, a tiny thumbnail size image. So it's hard to say, okay, maybe we have two images that are close to each other, and there could be some, but the number of pixels around the cell is still really small to have really valuable information from it. So it's better if we have an entire slide and we crop bigger parts, and now we have more global information. You can.
Yeah. Actually, it's quite different that, for instance, in pathology, when you study an image of a tissue, have some properties between the biological object, but here you are in the blood, so it's fluid. So I think the spatial relations between the cells is quite
in pathology, there is this architecture, like global architecture information, because for us, the cell move, not anymore when they are in the smell, but before. So there is no information about like, oh, these two are close, so maybe they are interacting or something.
Okay, thank you. Yeah, concerning the color transform, you apply a specific color transform to each sample in your data set, but I'm wondering if the color transform can also be adapted given the label of the cell. I mean, to apply different transform depending on, because you have a prior in your data set, the labels of the images of the cell. So what about adapting the color transform to the class?
Well, my first answer would, I'm not a biologist, but I think you really want to have a consistent aspect between the different images. For example, the eosinophil, which is really red, you still want it to be more red than the purple. So I think it's important that at least the different color variation among the label is different, because that also reveals properties, biological properties. So I don't know if you have something in mind in terms of which label and how, but I think it's really important that we keep actually this these differences of colors, because it's a lot of information for the pathologist, so I guess also for the algorithm. Yes.
Okay, thank you. I will move to the second part for the multimodal approach, where you combine handcrafted features with a convolutional neural network. My first question is about the impact of the segmentation results on your conclusion, because actually the quality of the handcrafted features is dependent on the quality of the segmentation. So did you try to to study the interpretability of the features by using the contour segmentation for the delineation of the self. I mean, instead of the predictive segmentation, just to use the contours.
To be sure. So first of all, there were many datasets that didn't have the ground truth. So that's the first point. And when I had it, it was in a few images. I think the maximum is one dataset has 1,000 ground truth. So maybe on this one we could have checked, and I haven't. But then the others, I think we have like 40 or something ground truth. So it's not so big. But that's actually a fair point because as you mentioned, there is a huge impact on the segmentation.
It's true that you don't have the contours everywhere. So.
No, yeah.
Okay. So in this chapter, you conclude that you develop a new approach. The new approach is proposed to have better explainability of convolution and neural networks prediction. But actually, in your method, you interpret the uncrafted features. You do not interpret the feature from the boundnet.
Yes, true. I see your point, but because they are concatenate. Yeah, I mean, of course there is and we actually studied it a bit further after, and like there is a strong specificity of like the features from the network and the features from the CNN and the features like that are handcrafted. But then because there is still a layer afterwards, and we guess the back propagation is going into two. So, but that's true. It's more the handcrafted features that are under interest here.
Okay. But yeah, actually, if you found, thanks to your interpretability study, that a texture feature is well adapted to a specific class, maybe it could be possible also to check if texture filters in the CNN have been also activated during the experiment.
Yes, it's and also maybe to look at. I've been doing some research after, and we're like seeing some cross attention about like how the features from the handcrafted part interact with the features from the CNN. You know, like yeah.
Okay, thank you. Maybe two last questions concerning the last part of your work. So I really like the idea of combining self-supervised learning with also domain knowledge. So congrats you for this work. So in what you did, you used some information about the hierarchy of the labels to guide the supervision of the model. I'm wondering if you can, if this would be possible to push forward this idea by integrating also domain knowledge in this graph of labels. Because, for instance, you have for each class, you have the label, and you maybe can map also this label to some semantic graph like QMLS, etc., to get the definitions, also the semantic definition of the classes. And I'm wondering if this also external knowledge would be also a way to help you in task.
Yes, I've been doing some research when I started with the hierarchy, because not in cytology blood, but in general, there is this idea of using the words embedding and then having a hierarchy in this like words space and using this for the training for images. So that's kind of text and image training. And this is, but I haven't trained it like this for multiple reasons. But I think also because we had some specific labels to ours, like sometimes it could be a large variant lymphocyte or something that I don't even know what would be the word's translation for it. But yeah, trying different approach for the hierarchy would be a nice idea.
So actually, in this chapter, you are working on representation learning, and in the literature, in general, when you optimize a backbone, it's kind of task agnostic, and then you can also evaluate your backbone on different downstream tasks. In your case, you evaluated your backbone on classification. Did you also try to evaluate it on other downstream tasks, like for instance, segmentation? You can use your backbone and you can plug it in a unit architecture and evaluate it in a segmentation purpose.
Well, no, and this is mostly for really practical reasons. It's also because this project was also performed in parallel with the Munich team, and we were all evaluating on the same task, because like it was also part of a bigger project. Yes, we didn't use it for the segmentation.
Okay, so last question, maybe a more high-level question. So you propose in your perspective also to guide foundation model with external knowledge, semantic knowledge, etc. But it's quite antagonist with what the GAFA want to do with very easy data-driven approach. So there is a balance on what you propose to do for the next steps and what the GAFA wants to do. So can you discuss a bit about it?
So, I mean, first of all, they have the luxury of having many data, which I think it's not the case for us. So even if you want good performance, you need some, it's better with some knowledge because we don't have as many data as they have, especially in cytology. Blood cytology it's smaller compared to histopathology, for example, in terms of availability of the data. So that's the first point. And I think I do not know all the details, but I think the medical application needs some strong proof, and that's would, I think, having more information and less data-driven approach, it also allows to weigh, even if maybe the performance are a bit lower at the end, it also allows to understand better which is weighting in the final prediction. So having hopefully some more explainability.
Okay, so thank you for your clear answers. I'm done. Thank you.
Thank you. So the next discussion will be with Sergio's. Sorry.
You can skip
Christo,
my
you just
Thanks for trying anyway. Okay. Thanks for the presentation, which was indeed very clear and well-paced and well-structured. I have several questions, some more technical, some more high level. I can start with a little bit some of the technical ones. For the first part, with the generalizability project. So you presented some results and some ablations on these different formulations that you did. Have you tried comparing against like foundation models, new foundation models, and what are their generalizability properties?
So the answer is no, because this was really beginning, so 3 years ago, and I think I was not at this moment. So yeah, the foundation models were not performing so great, but I haven't tried since being like, comparing with my workload. So
And maybe some details about the experimental configuration for testing and reporting your performance and generalizability. Did you use some kind of databases completely external from the training? How did you define the training testing setup?
Maybe I can just show you. Okay, you tell me if that answers your questions. Option. Okay. Yes, now we see here. Is this large enough? So I don't know if it's answers, but there were 2 data sets for the training. And then for each data set, so I don't know what you mean by completely external. It's never completely external in the sense that there is always a small fine tuning with 100 of images for new data sets. These are all different, so not seen for the training. And then there is the final testing.
Okay. Okay, it's clear. All right. Now a little bit, one bit more difficult question, which I guess there is no clear answer, but there are two different ways to tackle generalizability. One would be to try to standardize everything, and the other would be to try to enforce a lot of augmentation
Yes,
during training.
yes.
Have you tried these other kind of formulation, or do you have some comments on this?
So I haven't tried. I have tried the, let's say, standard augmentations, as many as you can. I haven't tried the GAN or like creating new images, especially because at this moment the purpose was really to keep it realistic looking, reliable and all. But yes, having a lot of augmentation is also a solution that works, and that's, I don't remember if it was working better, but that's a good question. I would say no, because in the ablation study there is without, I would say no, because in the ablation study there is without the color transformer with, yes.
Okay. Yeah, I mean, there is no one way to go. Okay. Moving to the interpretability case, do you mind discussing a little bit more on how you combine the different kind of branches between the CNN features and
Yes.
the other?
It's well, maybe it's a simple concatenation of the features. So yeah, at the end I have the two embedding vectors and I concatenate an additional layer of the file protection.
Okay, and then on this kind of formulation, how do you extract the sub values?
So my proposition, because the sub values as it is written in the library, it cannot handle multimodals. So I extracted a set, like I extracted only the part of the model that is without the CNN. I don't know if you remember my graph, and then I computed the sharp values on this network, and then I had actually the sharp values for the image and the sharp values for the features, and I keep them. I look only at the sharp values of the features.
Okay. All right. Then, so this kind of interpretability, if I'm not an expert, but if I understand correctly, hematologists, when they look on these little images, that should be able to very, very quickly and easily detect all the different subclasses. Is this the case?
Yes.
So can you use these types of interpretability kind of tool that you put in some sort of quality control for the performance, or how well the model is performing, or how accurate the model is looking at the details that needs to be looking at it?
And that was the point, yes. Then now I would say maybe social values is extremely computationally intensive. So maybe there are other ways to do that, because you should use it all the time for every model. I don't know. Yeah, it's just a matter of computation regarding to the. It's better because there is some quantification, but it's still not perfect. I mentioned it in the limitation of this part. So is it worth the computation? But that's another question. But yeah, that could be proof for some.
I just have a comment about that. So for the field, your sharp value doesn't mean anything. The entropy of the yellow color,
exactly.
this is a new semiology, but this is absolutely not explaining anything about how you decided.
Yes.
So I think it's a good idea to try to explain, but you are very, very far from explaining anything about how we interpret images. And so
So I mean, it was not coming from nowhere. It's like in literature, they can either use the images or the features, and when they use the feature, it's mostly this type of feature that they use, this entropy. But where you're right is they do not use it for explainability, it's more for classification, because they provide really high classification results. So they are still like good in terms of algorithmic. And what is interesting is because they are automatically extracted, so we don't need, because the annotation, but of course the ideal would be there is a paper that is using like biologically relevant features, and the ideal would be to have these biological features with our framework. But this is really, really long to annotate. We've started doing so, but it's a really, really long process.
I understand.
And I comment because, okay, it's true that we have used those special words, entropy, and what is specific of the texture is not well understand for cytologists, but maybe it's not very hard to translate it in a few simple words. We could make categorize of those, for example, the patterns, and we could make a simple kind of a classification of whether it's fine-grained or big-grained. I think because for the color, it's quite translatable and quite understandable, and the shapes. So I think most of the features are not that difficult to interpret. But it's true that for the pattern, maybe it's more like a vocabulary.
When you learn cytology, I think in 10 minutes you can all be cytologists. If I show you a eosinophil file, a neutrophil, and a lymphocyte, in 10 minutes, everyone in the room will be able to classify and to say why.
That's true.
And you took 3 years of work to try to do the same with the machine. And at the end, I'm not sure the result is explaining anything to us.
No.
So we are talking about
it's barely being close to what we think.
yes,
Yeah,
but it's very far from explaining something.
Yes.
Also, this is my point, the point of my question, because in essence, we don't really, or Manon does not really need to explain something to you, but it needs to figure out why the model is performing as it is, and maybe this can be used like as a.
I agree.
One,
it can be very helpful for you to develop new ideas and so on, but I think explainability to the clinician is very cool.
Yes, I agree.
And maybe it's not a problem, but we will come on that later.
Okay. Okay, moving to the last part, maybe, of the page slide. So there are different kind of foundation models that you can find in the literature. Some of them coming from like natural images. They're even domain specific for psychology and not, for example, dynamo.
Yeah.
So have you tried to compare the output of your model with these types of models to see how well they benchmark with each other?
Yes, well, so Dynamo is the model we were developing with the German team. That's the team I was working with. So of course, I of course compared with Dynamo, and then also that was more their part that they did before benchmark with like virtual, Punch, Uni, so other types of models.
But this hierarchical kind of loss functions were not included in the.
No, true. That's true. It's more because like we started by seeing that Dynamo was best working, so this is where we've been elaborating which I mean, it's been trained on blood cells and the others are trained on histopathological image, so that also makes some sense. But also, I haven't included it into the manuscript, but I've also tried to train without the Dynamo initialization, and the results are not so far yet, like with the hierarchical training.
And the way you were training these models were training, it was a fine-tuning step, or did you consider also kind of adaptation methods?
More adaptation because it was a long training, like 70,000 iterations, so it's not fine-tuning at this stage. And I was using all the data, so it's more like adaptations.
Okay. Okay, then the last kind of high-level question. there are kind of two different ways to work with lately with deep learning models, and one is going towards foundation models that are trained on very, very large databases, and the other is more domain-specific and specialized ones. And I guess there is a trade-off between these two. When you want to do something very specific, you might be better with the domain-specific model. So can you comment on what do you think, like in a few more years, we will be looking at in kind of this?
Well, I mean, the trend is also more, I mean, it also depends on how many computing resources you have. I really think that maybe the hierarchical setup could be, I mean, anyway, it could be introduced in any type of model. So it would be interesting to look at it in a smaller model. Here, we really wanted this open mind. I mean, the classification is of course lower in terms of performance than if you train a classifier. But here it's also because every time we talking, I mean, at least in the lab, and we realize, oh, but we forgot this class of cells, and oh, in this type of pathology, that could be, so this open world mindsets, which I think is really characteristic of bigger and foundation model. That was what drove me in this last year. If it's just for classification, that would be better to have a strong classification with like all the classes you could encounter and a lot of data, and having very domain-specific model that would, of course, give better performance. But for research and this open mind, open mindset, I thought was very interesting. Yes.
Thank you very much.
Okay, thank you. So it's my turn, probably. And so thank you very much for the invitation, for your PhD directors, and for you for the manuscript. It was really, really interesting to read it. It was very well written. I don't know if you used some AI to write that, but it was really, really cool. And okay, I had the manuscript in my bag for a few days, and there was a lot of rain in Lyon this time, but it's still alive. And I will keep it very in my office because it's a lot of information. So thank you very much. And your presentation also was great. I nearly understood the third part of your work, but it's still a bit complicated. But we need to discuss later. I need more dummy explanation to understand the hierarchical model. Okay. So I have a simple question to start, a basic one. You say that it can be useful to automate cytology.
To automate is the fact that when you look at the slides, you can have information about all the cells of the slide. So this is, of course, there are 2 points of view. Either it is for the routine clinic, you could say, oh, it's error prone. That's what you see in all the articles. It's pretty error prone, and maybe there might be something that the expert has missed, and now we can. So that's the first idea. Okay, as an assistant, being like warning, there is something here, just to be sure you haven't missed it. So that's to reduce the error. And then for more research, and I think that was more our point in these 3 years. But also the thinking now that we see all the cells in the slide, maybe we can spot some new things that we haven't seen before because we have large point of view.
Okay, so your answer is that you want to increase the level of cytology, either by detecting errors or some cells that we didn't look at, or in order to discover hidden information that a human is not able to detect.
Yes,
But all the work you produced aim at reproducing the cytology and not at increasing its accuracy.
Sure, but if you cannot even do what the experts can do, like you cannot go further, like there is also a first step that is, going, as you say, in 3 minutes you can do the classification and the algorithm is still not able to do it. So of course we cannot pretend to increase anything when we do not achieve this performance. No?
Yes, but if you try to mimic the cytologist, you will also mimic its limitations and its errors. So is it the good way, if you want to improve cytology, is it the good way to start with reproducing what humans do very well, actually? Or should you start on what do they miss? And this is where probably we can develop new technologies to fill the gap between in the space where we do not know how to do.
So I think it's important to mention that for now, I think the AI is not a superhero, and if the human is not able to do it, there is not a zero, but really little chance that the AI can do it as well. So that's for now, and especially we need the annotation of the human. So we need the human to be really confident about its own annotations for the AI to do something that is maybe as good. So the starting point is what annotation do we have that are available, and the AI try at least to redo what the human can do. Because even let's say the AI is really good and perform something that hasn't been done by the human, the truth is also quite hard. Like, is the AI saying hallucinating or is the AI saying something standard? So of course you can try to perform complementary testing, and I wish that would be the future. But for now, I think if the human misses it, it's gonna be extra hard for the AI to do it well.
Except if you choose a question where you have a label that is not cytology but something else.
Yes,
and there is a huge need to find in cytology some answers that humans are actually not able to say. So, for example, in acute myeloid leukemias, you have some genetic mutations that are important. You cannot see mutations with your eyes, but these mutations have an impact on the cytology that we are not very. It's not very easy to make the connections now, but probably there are some links that AI can detect. So it could be probably an even more interesting way to go to start on what human cannot do instead of starting on reproducing what human can do.
True, and this is actually a hot topic in nowadays, and just for example in the German lab, but also in other labs, of having this mutation information and trying to predict, and also some other where you use, for example, the immunostaining to be able to see some things in morphology that you couldn't see. So that are also other points. But the focus of this PhD was classification of cells. But I agree, these are really interesting subjects and promising. Yeah.
They are not criticism,
No,
it's just
yeah.
discuss. So also, why do we want to automate? Doing this kind of work uses a lot of informatic resources, so it pollutes a lot. So if we replace humans by machine, it will be cool, but we will have some people with no work, so no money to live. Instead, we will pay money to Facebook or Microsoft to buy their license to do a task that we perfectly know how to do with humans, and we will produce a lot of carbon and so on. So do you think it's really a good way to go for research to develop strategies that are mimicking humans, but with very strong consequences on the social and ecological aspects. You're younger than me,
Yes,
so you are
yes,
concerned by the world in a few years. So what do you think about that?
That's a large question. There are many
Yes.
things in it.
Yes, but
Yes. No,
it's an important one.
Okay, so first of all, for the polluting aspects, this is a real crucial part. But for the training, is polluting the inference is a bit less polluting, but it's still because, for example, electricity, water resources, and so on. So even if it's not perfect, so there's still some move towards smaller models that are consuming less, some fine-tuning strategies that are not using too much, and so it's that the thing is that we have smaller models, but then we use them more. So of course they are still they're polluting less, but because we use them more intensively, I don't know if it's a really lower pollution process. But that's a good question, because I think the systematic use of AI by everyone has really been something for this last year, and that was not the case at the beginning of my PhD. It was just like some research using AI, so it was not such a big thing that was such a huge ecological impact. So that's the first point. But then I still believe that, I did this PhD also because I believe it has some positive impact for the future. And even when I'm not a specialist in text, but when you see the progress in LLM and all, I still believe that it would be trying to close your eyes, not to use it even at least as a help, because that there are still some promising things that are happening, and it would be a shame not to having it. Then I don't know about systematic use in all the hospital. Maybe that's not the best way to do it. Also because, of course, there will be an imbalance between hospitals that can afford having the expensive software. So I do not do this political implementation. But for research, I believe it's really important. Like, it would be a shame not to use it.
Okay. I think it's important to have this kind of question in your mind, maybe for your career and so on.
Yeah.
But thank you. Another hard question is a very naive one. For human people, it's very, very easy to distinguish these kind of cells. Even a child of 3 years old can learn how to distinguish lymphocytes, neutrophils, and so on. It's very, very easy. For normal cells, when it gets pathological, it's a bit more complicated. But for normal cells, it's very easy. And really, while reading your manuscript, it was very complicated for machine to do the same task as we do so easily. So it's not to say that humans are still doing better and so on, but is it a conceptual problem? We work with segmentation, then classification, then and so on. Is it the good way to work? And in our brain, do we do the same kind of reasoning, or is there something we need to understand about the functioning of the human brain in order to solve more easily this kind of problem?
So that's a good question, because it's been evolving recently. So first of all, about the performance, it's important to say that I put the algorithm in specific situation where I knew it was performing bad. So the idea was to try, if I use a traditional classifier in the traditional way, you would have outstanding results, but especially for easy cells, because it's like 99.9, So, but here I put it under it's in the corner, like in the situation where it does not perform well, the generalizability, less supervision. So doing the hard part. Then we also use some classes from the marrow and some pathological cases. So they're not so also trivial. So of course, the first chapter is about like mostly blood cells, so it's pretty easy to distinguish. But the further we go, especially when we go in the hierarchical differentiation, the last level, for example, the abnormal and normal eosinophil are part of this hierarchy. So this is much less trivial part. So I don't think it could be such an easy task. And then this is very true. I mean, this is what happens with the foundation model, even if it's a big word, but that's the idea of like, we do not give it a label anymore, neither segmentation nor classification, nothing. But we need an amount of computing resources that's just huge, but we like, now that we have the luxury of having so many data, so many computing resources, we just put everything and we shake the thing of, oh, well, that works, but at what price? But yeah, true that now having new way of training actually shows really interesting performance. So.
But the brain of a human being is working with very low resources, just some glucose and it works. So, no, but really, so why is there such a big difference between our performances and the performances of machines? Maybe they don't have some ideas of the world, some concept. Is it what is lacking? And can we put concept in the machine?
I know that the purpose now we're having what we call the model moves, world model, where the idea is that having something that could be closer to the human brain and understands everything. But I think, you say it yourself. It's amazing what the brain is able to do, and we're still beginners trying to do hence of what it's doing. Then I think it's also important to mention that that's something that the AI does well. For example, data resource, like they can gather and understand a huge amount of data that the brain is not able to to do. So it's not like it's also another type of evaluation that we are having now. It's doing something else that the brain can also do. So.
And in your work for your PhD, for example, did you speak with a specialist of human cognition or human vision or animal vision to have some ideas about the last discoveries, to understand how our brain is working, and can it help you to develop?
But no, and I'm not exactly sure, but I think there are some research about like, AI neurology, kind of like having exactly the functioning of your brain and trying to put this in the knowledge of your AI so that it understands better. But I don't know about it. As to be honest, if it was working really well, everyone was worked well. So now what works well is what we are doing. It's convolution. It's deep learning with activation.
But maybe it will go to a plateau, and then to go to another thing, we need some new ideas. So maybe we need to search that elsewhere.
That's interesting. Yes.
Okay. So last question, it's a remark about explainability. You say that it's important in medicine, but I will say that in medicine, most of the time we do not really understand what happens in patients. We do not know why paracetamol is good for fever, for example. And this is not really the problem. The problem is trustability. I want to be sure that if you have fever, I give you paracetamol, the fever will go down. But it's not a problem if I don't know the name of the receptor where the molecule is binding and so on. So I'm not sure that explainability is so important, but trustability is. This is not my idea. This is from a friend who is working on this question. He's a philosopher of medicine. And probably the first part of your work, which is how we can develop tools to normalize the prediction of AI, is even more important than the second one about explainability, the shelf values, and so on. And as I said before, shelf values is a kind of new word for us and not explaining many things. So probably it's okay if in medicine, it's okay if it works, even if we don't know, if we don't understand why.
Okay, I agree, but in a way, I feel like all the practitioners I have been interacting with, they want to know why. Like when you show them it's true. It's the paracetamol because there's been a clinical study that have been showing that significant, But for us, AI, well, I mean, sometimes there are clinical studies, but not all the time as well. They at least in the research process, they really want to understand what's happening with them. Yes.
But even if you explain why it works, you will have to demonstrate that clinically it works. So you will have to make clinical trials or things like that. So I don't think explainability is such a problem.
Okay, no, that's an interesting point. But for research, I just feel it's important.
It's very important for you to go first.
Yeah.
But for clinicians, we are used to do things that we do not know really well why it works, but it works, so we do that.
Okay.
Okay, so thank you very much for this very interesting PhD. And then Daniel or I don't Daniel.
Thank you very much. Yeah, we'll just give a few words on how happy and very lucky I had that you chose our subject and that you came both in our lab. It was really fantastic for us to work with you. I learned more in 3 years than probably in 10 years on AI. And what is the most amazing about you is how the good mood you always have. That's amazing. I mean, everybody can witness this. Even though you had difficulties, okay, you always continue to move and find solutions by yourself most of the time. And that was also really amazing. So as a co-supervisor, it was really easy, but also very nice. And I was very happy that you were able to do, even on your third year, something different that you also choose, try to help as much as we could. You did almost everything by yourself, even writing the papers. So yes, thank you very much for working for us and with us, and I wish you a lot for the future.
First, thank you all, you members of the committee for attempting to read the thesis and to be here with us. Thank you, Daniel, for this 3-year adventure. Maybe I can recall that this thesis was founded by SKY, which is the Sorbonne University Center for Artificial Intelligence. One of the area at SKY is health applications. So obviously you're part of this area within SKY. You also participated in SKY by giving some trainings and some different talks. It's probably not necessary now to emphasize again how cross-domain the thesis was, because you made it very clear and the questions highlighted that. But maybe I can recall that for you it was also a physical reality. You spent half your time here at clinics, half your time at CRSA and the other side, and time in Munich as well. You really understood this thesis as cross-domain. You talked with a lot of people. And maybe that's an opportunity to mention that you participated in different side projects that are not in part of your thesis, and that's often a good sign. When it's the case, you gave some courses at the university. Maybe the most difficult part was not to give the courses, but to get paid. Maybe that's my question, my only question. Have you finally managed to get paid at the university? maybe that's your only fate with this thesis. So, and so maybe more importantly, you spent about 3 months. We cannot not sure they are here online to listen, but I'd like to thank them for welcoming you and for this work with you. So it's never easy. This kind of thesis, especially, is never easy because you had to deal with two labs, two domains, two cultures, and with the confidentiality of data. So it was not the easiest part as well. But as Daniel said, from our point of view, it was easy because it's quite easy to be your advisor. You had this meeting. The first thing of the week was our meeting, and Monday at 9, so not an easy slot. And well, basically, we just had to bring the coffee cups, and we brought the idea, we brought the work, we brought the results, we brought the questions, and even when it was difficult, when the results of the experiment was not as good as we hoped, we were looking for the next move, for the next experiment, for the next step. So thank you for that. You also have been an important member of the lab. I think people behind me can agree, and you contributed greatly to this positive atmosphere among the students, among all the members. So thank you very much for that. Maybe Cecilia and Stanios, if you don't mind, I'd like to repeat that just shortly in French for the public and for maybe for Manon's families. Donc, je voulais redire que c'était un plaisir d'avoir vécu ces 3 ans avec toi, que tu as été force de proposition en permanence, que ta compagnie a été relativement simple et que même si, comme dans chaque thèse, il y a eu son lot de difficultés et de doutes, tu as toujours été très efficace, pleine d'idées. Tu as, je pense, profité de tous les aspects d'une thèse. Une thèse, c'est un manuscrit et une présentation. Et ça, c'est au jury de dire comment ça s'est passé. Mais c'est aussi plein de travail à côté, des expériences qu'on ne va pas mettre dans la thèse, des gens avec qui on discute, beaucoup de gens avec qui on discute, beaucoup de rencontres, beaucoup de voyages, beaucoup d'aide. Je pense que tu as aussi beaucoup aidé les autres. Et donc, pour tout ça, c'était une thèse pleine. Donc, bravo. Merci.
Okay. So I think now we need to deliver about your PhD.
We're going to change and to go to another room.
We move?
Yes.
Okay. Perfect.
Cecilia, we are going to move, so we have maybe a 5-minute
5 minutes,
break.
okay.
And you can
We meet on the same link, okay. So, shall we meet in 5 minutes?
Yes, 5-10 minutes. You can have a break if you want.
Okay, thank you.
Je veux juste vérifier qu'on n'entend pas. J'ai coupé le son.
Moi, je suis partie.
D'accord. Là, on n'entend pas. Hein.
Je sais que
C'est juste pour m'assurer que j'avais coupé le son.
Merci.